So let's get started. I'm happy to see so many of you here that are interested in simulating the city of the future. My name is Franziska Hunger. I'm a researcher at the Fraunhofer-Chalmers Center for Industrial Mathematics and one of the leaders of the Digital Twin City Center research area on simulating and modeling on the city level. So I am honored to chair this session here today, and we have a very interesting and great lineup of presenters that will walk you through the current practice of simulations, future research on what will be doable within some time, and applications to climate adaptation, to natural hazards, and generative design optimization. So we have a quite tight schedule, so we will run through the simulation, through the presentations, and have questions and answers at the end. So first, I'd like to introduce you to the researchers from the Gates Institute that will show us some different applications using computational fluid dynamics. This will be shared between Maria and Radosten.
Thank you, Franziska.
Thank you. Okay. Right, so we are Radosten, and this is my colleague Maria. We are from Gate Institute from Sofia, Bulgaria. The institute was founded in 2019 in collaboration with the TCC, and it aims to develop big data and AI applied research. We are working in the focus area of the city digital twin, which includes CFD simulations. So first of all, just very briefly what CFD is, for those of you who are not familiar with it. CFD stands for computational fluid dynamics, and it basically allows us to solve any problems involving fluid flow. This can be used, it is widely used in the aerospace sector, automotive sector as well. It can be used for wind turbines, combustion in engines as well. But in our case, we use it for simulating buildings, for wind flow around buildings. Now a little bit more about the CFD and how it is applied in the area of city digital twin. There are different ways, there are different applications, and some of them include urban planning and design, air quality analysis, pedestrian wind and thermal comfort, cultural heritage preservation, solar potential analysis, and urban heat islands. These are just a few examples, and we'll take a look at some of them right now. So here we have one of our use cases that we have been working on recently. We call it the GOCO case. It focuses on an area next to south of Gothenburg, which is down there. It's actually GOCO Health Innovation Center. Here's a closer look at the area. And so from this, we created a 3D model of the buildings and the terrain itself. Then this is the area which we're going to focus on, and we performed a wind comfort study using IBOFlow, which is developed by our colleagues at Fraunhofer-Chalmers. The initial goal of the study was to determine how many wind directions are actually sufficient for performing this wind comfort study. Because as you probably know, CFD can be quite computationally expensive, but we also require good accuracy from the results. So in this case, you can see the results with different number of wind directions. So here we can see with 8, 16, and 32. And we concluded that 16 wind directions are actually accurate enough, and they require less computational power than compared to those on the right. Another part of, actually, you can see the legend. So the darker blue color represents areas which are more appropriate for sitting long, for example. Then lighter blue represents areas which become more windy and where sitting short is actually recommended. And as you go further to the color scheme, for example, red signifies areas where it may be uncomfortable or dangerous. In this case, we don't see such areas. Next, to build on our study, we chose one building in the area of interest. It's the selected one over there in dark blue. This is a closer look at the building. And we wanted to see how, if we can perform such kind of studies in an earlier stage of building design. And so we created a simplified version of the building, which you can see there. The way we did this simplification was we got the footprint of the building and just extruded it up to a certain height. Next, we compared the original results with the simplified ones. Here is actually, you'll not be able to see this. Okay, so the building, the simplified building is actually this one. This is the original, and over there is the simplified one. And here we can see some very minor differences in the results. We concluded that the results are very similar, and this actually confirms our hypothesis that CFD can actually be used in an early stage design. And from here on, I give the word to my colleague.
Thank you, Radi. So the next study I would like to present covers an area from the city of Sofia, which is locating around the new building of our institute that you see here. It is mainly about urban ventilation and pedestrian comfort, but it's actually a bit more. This is a very interesting area to study because we have a lot of different occupant types and a lot of different urban use cases. We have university campus, actually, a couple of them. We have primary schools, retails, and housing estates. We have city parks and roads with busy traffic and public transportation stops. Furthermore, what you see with the icons on this picture is our sensors from our City Living Club. So we can get environmental data from them and also data about noise and air pollution and pedestrian counting, and we can use them to input our simulations, or we can use them as validation points. And this is actually a very good case to show how we can complete this cycle to enrich the city digital twin with simulations data. Starting from taking the initial data from the city model, it can be geometry, it can be meteorology data. We make some pre-processing if necessary. Then we continue with the computational mesh, which is required for solving the fluid dynamics equations. And finally, we get to the simulation results. You can see here results for the wind flow in the city in terms of streamlines and also in terms of a contour plot. But this can also be temperature distribution, it can be solar radiation, or noise, or pedestrian comfort, whatever. And finally, we get these results back into the city model. And right now, this connection is static, so we have only one iteration of this cycle, but we have plans to make it dynamic, and I will talk a bit more about this later. The next case is a specific one. It's about cultural heritage preservation, and either outdoors or indoors, these structures should be able to withstand the environmental exposures and also aging, and while carrying their historical and cultural value through time and to generations. And this is where physics-based simulations can be very valuable to such cultural heritage specialists to help them understand and predict the deterioration in materials and in structures caused by different environmental exposures. The case study here that we have is based on a castle located in Lesbos Island in Greece, And this is an interdisciplinary study involving specialists from different areas such as data analysis and AI, computational fluid dynamics, visualizations, and cultural heritage preservation. You can see the partnering institutions above, and of course also Gate and Chalmers are involved. We have created the computational model to assess the effects caused by the effects of erosion caused by the wind, but I will not have the time to go into details about this model. If you're interested, you can find more information. We have one paper already published, and now we are making a more in-depth study to put a context of how wind flow and wind pressure on walls and the CFD results can help identify the critical zones in the structure in terms of erosion, and how these can be input into a comprehensive framework for risk assessment and degradation analysis for cultural heritage. Furthermore, these physics-based simulations can be used by the conservation specialists to test their mitigation measures and see how they perform virtually first before their application in practice, because usually with such slow processes like erosion, the human lifetime is not enough to assess their effectiveness. And to summarize our overview, the CFD simulations can be used to enrich the city model with physics-based analysis data and predictions about our surroundings, and that are directly connected to our comfort and well-being. They can help optimize the urban planning for improved natural ventilation and air quality, and can show how the best to harness the solar potential to increase energy efficiency. They allow performing what-if scenarios and testing a solution first virtually before its application in the real world to save time and minimize costs, and provide insights into very specific applications such as the cultural heritage preservation. And they also support decision-making, which is scientifically based throughout the whole life cycle of the city, through the design stages, operational life, and regular maintenance. Our future work at Gate Institute involves first working on improving the integration and visualization of CFD results into our city digital twin of Sofia. This is an ongoing work. And the next step would be reduced order modeling. As it was mentioned already a few times today, such simulations require a lot of computational time, a lot of computational resource, and also they require an expert to perform them. So a remedy here is a reduced order model that is trained on the simulation data. And for example, we have one or two varying parameters there, and we get close to real-time results. Once we have such model, we can feed it with the data from the sensors, and then we can have interactive results and live connection for a city digital twin at its full potential. That was all, and I would like to thank you for your attention.
Thank you very much. Next on stage is Maha from Right Architects, who will walk us through a case study on generative design optimization.
Yes, okay, that works. Good, thank you, Francesca. Hello, everyone. My name is Maha Shalabi. I work at White Architecture. It's an architecture office. I'm based in Stockholm. And I'm presenting today collaborative research about multi-objective optimization through generative design, where we have worked to optimize different factors, including daylight, electric light, energy, and CO2. And this was a collaborative effort between my colleagues and I, so I'm representing all of them today. And we haven't applied this into a digital twin platform, but we aim to inspire this so that we can apply this in the future within the digital twin domain. So this is a case study of an office building that we were designing at White. And actually the research, this is an internal research project at White that is internally funded, but it started with another research that I've worked on where we have simulated different parameters on a single room level that included also the energy and the daylight and the CO2. But then for this research, we have only looked, or we have focused on one floor plan, and we haven't taken the whole building because we were expanding from a single room to one floor plan. And the aim was to optimize the envelope design. That was the main aim, to inform the architects of the best window-to-wall ratio and the window positions. And we have varied different parameters that included the window-to-wall ratio, window positions, and the electric light dimming, whether we would have dimming or not. And the output, we have focused on the total energy use, total carbon emissions, the daylight factor, and the spatial daylight autonomy. So what we have done, the process that we have followed, is that we have first started to generate a base case or a base reference values for both the energy and the daylight. So for this floor plan, what we have done is that we have simulated one case without any windows, and we said that this is the minimum energy and CO2 that you could ever have for this floor plan. And we did the opposite for the daylight, so we have simulated the floor plan with 100% glass all over, and this is the maximum daylight that you could ever achieve. And then we have set up the logic. We have used Grasshopper and Rhino to do that. Where we have done is that we would do the simulations, and we have run it with a tool called Climate Studio, which is also in Grasshopper and Rhino, where we'd simulate the results and subtract it from the base case to get a difference. And we would use this difference to load it into another tool also that is called Opossum. And Opossum uses generative optimization. So it's like a smart solution that uses a bit of AI to generate the best solutions depending on the inputs that you have provided. So we were trying to minimize this difference. So what we were trying to do was basically minimize the energy use and maximize daylight results. And also, of course, minimize the CO2. And so that was our objectives. And then we have also had different variables, the facade logic and the dimming, which I will explain more. And the results, like I've said, we have looked into the energy, CO2, and daylight. Yeah. So this is an example of how one of the facades looked like, that we were doing it parametrically, changing the window-to-wall ratio and changing also the positions of whether where the glass versus the opaque areas are. And we had a glass module that was 5 meters in total, with each glass module of 1 meter, where we have applied like a random pattern so that this pattern changes throughout the facade in the different orientations. And then we have used this to build an energy model. And if you're familiar with how we build these energy models, they need to be as simple as possible. So they need to be just close volumes for each room. And then we have taken that and built on it a simple daylight model. And usually the daylight model is a more advanced model in comparison to the energy to get more accurate results. But for this simulation, we have decided to make it as simple as possible. So this is a new workflow that we have developed. So what we have generated for the daylight is that basically we have extruded the external walls to just have a bit of thickness, but then we have left everything as simple as possible. And we did that to speed up the simulation process and to be able to easily compare and load or run the iterative simulations in parallel to each other. I'm not going to go through this in detail, but one big part of the research was also to how to visualize the results. And what Opossum does is that it runs all of these parameters and tries to give you the most optimum solution. So in A1, the part that you see above, how can I do this? Yes, here. In this part, in Opossum, it generates the number of solutions being like starting with the best solution in the top, and then it gets worse, basically. So what we have done is that we have used Opossum for the simulation, but we have used another plugin called Walacy for the visualization. And with Walacy, there is an option to manually select the data that you want, the data that is generated, which we have done here. So we would export, or we exported the results from Opossum through Excel, and we would search for specific like solutions that we want to get and manually select it. So for example, if I select like number 5 here, it would give me the results for that specific solution. And Walacy could also give other options for visualizations, another one called analytical data selection, and that is something that is preset in Walacy that selects for you the most optimum solution. And then there is another thing that we have developed, which is selection based on a data range. So you can go and in this and say, okay, I want energy between this value and this value. Show me all the results that you have simulated. And this is an example of how we have visualized the results. So we have the simulation run with 800 simulations. So of course, it's a lot of data to process, and we didn't want, of course, to go through each and every one of them. But Opossum has made it easy for us, because then starting with the top, then that starts to be one of the best solutions. So with this approach, we have used this manual data selection over here to generate all the results that we want. And this graph shows a parallel plot diagram showing the minimum energy, the maximum daylight factor, and the spatial daylight autonomy, but also the minimum CO2. And this line over here represents the results for this specific case, which was number 5. And it was not number 0 because we didn't set in the script that you need to have a window in every room. So the best solutions in some cases did not generate any daylight in any rooms because there were no windows. So we had to choose solution number 5 as the best one. And this is the daylight. It was really, really good daylight results that we achieved in all the rooms, considering that we have another building here in the front, and also for the daylight factor. Another diagram that we have generated is this diamond chart, where the closer the results towards the center, the better. And I will show you another example which was not very good. So of course, this is the most optimum solution that was generated in comparison to all the other solutions. And it has the maximum daylight factor over here. And the third way to visualize the data was this graph, where the closer you are towards the center or the origin, basically, which is over here, the better the results are. And this blue dot represents this specific case. So we can easily compare, like when we were comparing the different facade configurations, we could just select the cases that we want to compare based on the list that we have got. And then we would compare between the different daylight and compare between the different energy, but also compare the facade designs, which one would be more realistic to have in such a big building, and which one would the architects be more interested in. So the tool helped us not only to look at the data and visualize it, but it also helped us to inform the design in the project. And this is a similar case, but I will go to that case, which is case number 561. And that was like a middle generation in the, of all of the, it was generation 25 of 54. And in that one, it included dimming and electric lighting. And this had a very high daylight, window-to-wall ratio, so it's higher in comparison to the best, which was number 5. But it had bad rank in all the categories. So you see this black line over here. This is the case that we're looking at now. and it's represented by this blue dot. So you see it's around in the middle of all the simulations that were generated. And this is also the diamond chart that I've shown you before. So of course, it's very far from the center. So you see that this solution is not a very good solution in comparison to before. So that's what I mean, that we can go in and check, okay, how does the different how did the different facade designs changed, and how did that influence the different factors, and then make informed decisions about which design decision to make. Yes, that's it. Thank you.
Thank you very much, Maha, for that interesting application case. And now Tara Wood from Rambo will show us how to approach the simulation for underground and natural hazards.
Thank you. So my plan is to delve a little bit into the research area simulation, district level simulation, but with some examples of where we're at now as a consultant in industry, and kind of bed the way for Minna, who's also a research lead together with me in this research area, and where we work on this milestone project together. And I added in the true. I was really glad to hear the presentation earlier, where this need for simulation and data to make something be a digital twin, and it's something that we at Ramble struggle with a lot, where just models aren't twins. You need to have the data in there, and we need to be benefiting from the value of that data by the power of simulation. So a little bit why we need to do things differently. The value we can see when we use data in different scenarios, the interoperability, but the need for validating the simulations, and a little bit about where we're at now and starting to implement in our projects, thanks to the research collaborations with Chalmers. So obviously we all know we have data and we have a prognosis. Maybe we're a little bit unsure about the error or potential error in that prognosis, but at least the data we can see, we have an outlier, and when it comes to the temperatures in the seas outside of Sweden, which is obviously worrying. And when it comes to, I work within transport, so our aging infrastructure and urban planning of our cities, it's very worrying when our sewage systems are also old and lacking capacity, and a lot of these issues lie unseen below the ground. Connected to that, in Sweden, we're due to grow by 30% in the sort of timescale that we talk about when we talk about urban planning. Obviously, we're going to have to build new structures for this, and we're also going to be reusing and adapting older structures. But we also now have many cities like Gothenburg and Stockholm and Uppsala that have very ambitious climate goals to abate the climate crisis, carbon neutral to 2030. And then also we see the importance of people and making this people be an important place. So what else are we not sure about, and why do we need to do things in a different way? Well, we don't really know either how we're going to live in 2100. And if we look at, the first railway in the west coast of Sweden 100 years ago, I don't think they would have perceived what we have now. So how can we think we know what will happen in 100 years? So again, we need to work in different ways. Obviously, Ramble's a consultant here in Sweden, or global consultant. We collect all sorts of data that we work with. We have our mobile mapping data, and we've had a project here in Gothenburg where we've scanned all of the streets and buildings and infrastructure. We have our Raptor, which measures the deflection of the road in moving traffic. From that, we simulate the bearing capacity of the road systems, and this was an example done to check if we could get wind farm turbines along an existing road safely, and if there needed to be reinforcement done, where should it be done? And we have groundwater data, we have monitoring data of movements. There's photogrammic data, of course. And we have these extreme events that happen now and again, like the landslide that cut off the main artillery between Gothenburg and Oslo. And of course, there was data that maybe could have indicated there was some sensitivity there. We have the INSAR data available to us through the Copernicus project. And there's some red dots there saying this ground is soft, it's settling, it's somewhere to have a bit of a red flag. But there is so much data, and I guess one of my frustrations in life is it's not available typically when we want to work with it. It takes a lot of effort to connect the dots between the data. I would love to say we work like this in all projects. This is the connected data and simulations within the underground. And of course, if you have this single point of truth, the same data can be feeding into other simulations as well. But I'll be honest, we've managed to do this in one project so far. And as I said, it's because it's so difficult to always get hold of that data. And one of the reasons why it's so important when we're talking about developing our future cities and making them resistant to what the climate is going to throw at us, and our urbanization and intensification of high-density living, is there are so many risks there. And if we're not aware of those risks, we maybe develop in the wrong plots. We maybe create more problems and hazards than we solve. So it's an important area to focus on. So what are we doing? Why do we say 4D digital twins? Well, if we're talking about the ground and soft soils, we have to go back in time. So when we're simulating, we're going back literally hundreds of years using the mapping data, which today quite a lot of the cities in Gothenburg and towns have this available digitally via Länsstyrelsen. But it also is telling us where the obstructions will be. There's an awful lot of timber piles under the ground in our cities, close to the waterways. There's a lot of long-term movement and activity due to us humans doing what we do. Here we have a roughly 150-year-old building in Gothenburg, where you see an example of using this LIDAR mobile mapping data, which was done for something else. But because it was available to us, we could use it to look at what is the current damage assessment of the buildings in for the future development of this place. And in some cases, when we're doing something very unique, then we have to put in a little bit more effort. So when we come into high-rise and there's other things come into play, it becomes very important that we don't just design according to the Eurocode loads. We use realistic wind loading, because otherwise we end up over-designing. That's not good for our economic or ecological sustainability. So we use a lot of very carefully validated simulation, CFD simulation models that have been validated both in multiple, I think it's up to 7 or 8 wind tunnel tests with a lot of sensors, a controlled environment, but then also in real data, real life data. The problem with real life data, there's often not enough data, the sensors aren't in the right place, and so on and so forth. And then that data, those simulations are then connected to the simulations below the ground with finite element modeling, where we can look at things like settlements and structural loads on foundations and piles and so on. So we have an example here where we used the historical maps to create the movements, the ongoing settlements that occurred in the ground based on the development of the city from the 1700s. We then checked that data against the published data that was available on the Läppstift in the background there. And this was used to then simulate, at that time, the ongoing construction of the bridge, where we had 5 years of data to again validate. And then we could use that to say, well, we were getting a more reliable simulation here because we've checked it at laboratory scale, we've checked it at full scale with different time spans. So now we're going to simulate our structure. When it comes to, as I said, piling is a big pain in the ass in a lot of projects in Sweden because we get so much movement caused by piling. And obviously, we can automate some of that, and we've done some of that in some projects where there's multiple plots due to be installing piles and who should do what where. By doing these sort of simple calculations, it's helping navigate the planning of how can this actually be done and what the actual cost is. A precast concrete pile is 1/4 of the cost of a steel pile, which is the typical thing you have to change to. And really seeing the risks and where you're going to have issues by both seeing the ongoing construction site above ground, but also what's going on beneath. As I said, if we have the right data and the right validations, then we can do really cool stuff. I mentioned the wind tunnel tests earlier. Obviously, that can be used for looking at extreme events when it comes to weather. And at the bottom there, we have also an extreme wind and air pollution issues created by grain that gets pulled up into the wind in a port. I mentioned that we need to invest in our infrastructure, not least our sewage treatment works, where they know they have data that their flocculation reduces the capacity. What do we need to do to redesign it? Well, we can do that with digital test beds. If we have we have a lot of projects where we're increasing the levels of our quay wall structures in order to protect against this flooding. But all of these different sorts of data we are inputting into a live model. We call it observational method. And that is being used to do scenario prognoses. What happens if we do X, Y, Z, or Q? But it's got a human input. And then if we look at our big sort of extreme events that we consider and we want to try and at least maybe not avoid them, but reduce the impact of them as far as we can, hopefully reduce them. And then you add to that the layer of, well, what's actually going on in the ground. So this is an INSAR map of Gothenburg, where red is it's settling a lot and green is it's not happening much. And as you can see, there's a lot of areas that fall outside of this flood zone that haven't been considered. And if we add on those other areas where these settlements are ongoing, you'll see there's actually a large percentage of the city that probably is at risk, but that we're not aware of. And then if you show the same idea again, this is some work we've been doing for Framtida, where we've done cloudburst assessment risk, where we've got the data from Gothenburg on the buildings and where the entrances are. And from that, we've come up, green is good, there's no problem. Orange, there's a bit of water, it's not too bad. And red, they need to do something. And if we look at that property and how the water would look from this simulation, and say, okay, they can put out some sandbags, they can deal with that. But if we add in the ongoing settlement that's occurring outside of that structure, then it's about 0.5 meter and maybe won't work with the sandbags. That's somewhere where they probably need to think about another solution. So we need to have the right data to take these assessments from. And then you say, well, what's the right data? It's a very good question. There's so much uncertainty in a lot of the things that we work with when we're talking about the below ground, and not least all of the whys we started with as well. We have had some research together with Chalmers, a PhD who's now completed, who's been utilizing data assimilation. We started off wanting to do an AI project on how road embankments behave and how we can optimize those. We didn't have enough data, it was too scarce, it was too poor quality of the description of the place or just the data in existence of the ongoing assessment. So we moved towards a data assimilation instead and using this Bayesian updating. And what does that really look like? Well, we start off with a large uncertainty, and for each data point, the simulation improves. And it means that we get a much closer to the truth and a known uncertainty. So this is something that I really hope to see in the future, and that we talk about probabilistic digital twins, and we really know the error in the data and the simulations we're looking at, and it's very visible to us. So I'll just finish on, we've spent a lot of effort to try and get relevant test beds within our milestone project. And these are the 4 test beds we're going to be investigating or are currently investigating. And Minna's going to give some examples of some of the work that's been done in some of these after me. Thank you. So.
Very much. Thank you, Tara. And she already prepared the ground for our last speaker, Minna, who will be presenting the recent advancements in simulating the underground.
Yeah, so thank you very much for asking me to talk about. So I'm pretty much continuing and describing the sort of research which is background on solving these problems which Tara was identifying. And my title is called Towards 4D Digital Twin for Underground and Natural Hazards. So we are going out underground. So what I'm going to be talking about, after very brief background, some of how we are actually nowadays modeling regional subsidence, how this pile installation, which Tara was talking about, how can we model the impact of that, and how can we assess landslide susceptibility, and finally looking at how we can integrate, like Tara was actually showing example of models and monitoring data, and then I'll finish with outlook. Now, what do I mean by 4D challenges? So my fourth dimension, world is three-dimensional, but my fourth dimension is time. And things change in time, just like, the cities evolve and we are doing different things. But the problems in the underground are something which is totally, largely ignored in most of the planning. So we are talking about large volumes of underground space. We are talking about properties which are evolving in time, very sort of uncharacterized, highly variable materials, harsh environment for sensors, so it's not so easy to know what's going on there. And also that existing objects, which there are plenty of, as sort of this image I got from Keller is illustrating, we don't actually know exactly where they are. And yet we are sort of having these new problems of infra being aging, urbanization, climate change, and energy challenge. And I was quite positive that underground has been getting a lot of international fuss recently when there was these sort of dramatic articles of pretty much scientific nonsense talking about New York City sinking due to the weight of the skyscrapers. But in a way, they were talking about millimeters and how that affects coastal flooding. But then sort of we go to Gothenburg, where we are now. And I mean, these are all these examples of what are the planned developments. I got it quite a long time ago. And what we noticed that actually quite a lot of red buildings, which should have been already ready, are not that year. So there's plenty of projects which are cancelled because they didn't think about the ground conditions early enough. And everything turned out to be more expensive. I mean, we can construct on anything, but it's just about money. And usually we don't have endless money. Tara was already showing some of these INSAR measurements, so how the city is subsiding. And if you sort of look at that map where all these developments are and look at the red dots. So basically we have these areas where we are planning to do everything, that's which are subsiding the most. And that is without us doing anything. So if we start modifying, adding fills in order to prevent flooding, we actually are creating the worst situation. And any of the flooding scenarios don't take subsidence into account. Not even in this current situation. Well, related to that, we actually have a research project where PhD projects where we are trying to sort of look at a more sort of comprehensive way of modeling subsidence, also accounting for the fact that, it's not just the current scenario, but if we have infrastructure projects where we have some leakage, like tunnels underground, West Lincoln, or some pipe works underground, under the streets, we need to know sort of what is sort of the effect of it, and if we have subsidence, how much time do we have to react to it. So we need to start with the 3D stratigraphy with groundwater levels, but it would be too consuming to try to do a fully coupled three-dimensional flow deformation model for a large region of a city. And that is in a way why we sort of end up simulating selected two-dimensional cross-sections with a fully coupled model, which we then use to train and tune a surrogate model. So basically we are using machine learning techniques. And then sort of we can link that to, for example, future building damage. And the reason we need to do it is that in Gothenburg we have a very variable ground conditions. So we have these bedrocks which poke out, and then we have very deep clay deposits, and there is a possibility for water to drain underneath the clay, which basically causes very deep subsidence, very deep down. Calibration of the model is an interesting thing, and we were quite lucky that we are looking at the Haga, Vasastan area, and the nice thing is that we already had sort of validated that we have quite a good system performance for the Göta tunnel, but that was a 3-year construction time. So now we are looking at longer perspective. So how do we know that our parameters, especially when we know that anything, what samples we take deeper down in the ground, they are very susceptible for sample disturbance. That is in a way where we have to validate against measurements, and in this case we were very lucky that we had a bellow hose, which is basically measuring how the ground is settling at different levels, very close to where basically the Västerlänken tunnels are. And we were basically playing back in time to see that we are tuning our parameters so that we are able to model this performance. And then sort of once we were happy that, then we can sort of do subsidence predictions. And here you see that in a way, even if we don't do anything in this area, there will be sort of areas where we will have sort of 25 centimeter subsidence. It's quite a lot. So in a way, it is something that we should not ignore. And with the meta model, we can get sort of ideas of what is happening in 30 years. And of course, if we talk about just what's happening in terms of subsidence, there is actually quite a strong linkage between the clay depth. So very simple things would help in planning if you would even just put a layer of clay depth before you start your projects. Tara was mentioning ground movements from construction activities, and especially when we have these great depths, there's no way that we can build houses or anything on it without actually putting some piles underneath. So typically on this, when you look at läppstiftet, etc., you see a tall building, but you forget that there's a lot of stuff underneath. I mean, about 30% of a concrete in the world is underground. So talk about sustainability, don't build on soft clays. This condensing urbanization has its carbon budget. So we need to have these piles, and it is actually quite shocking that in Sweden we are actually installing about 2,500 kilometers of piles per year. So it is a lot of carbon which we are hammering, or actually just gently pushing in the case of Gothenburg underground. And nowadays, with the modern computational tools, it is possible to model this pile installation. I mean, especially for single pile, as part of one of the PhD projects, which is forming part of this digital twin city center together with the NCC. So we can model this pile installation, but of course, then sort of when we have tens and thousands of piles in a very short area, we need to look at that as well. So typically for planning, etc., it is really subsidence, flooding, and this issue about construction affecting existing buildings, what we need to look at. But then in a way, we are on the island of Hisingen. 1977, 8 kilometers north from here. 5 to 6 minutes it took for 9 people to die, 60 people to be injured, about 500 people becoming homeless because of quick clay landslide. So we are living also in a very dangerous area, and we should respect what is underground. And Tara already was showing this E6 disaster, which was the most recent one, which of course, in a way, we were very lucky that there were no casualties or major casualties or loss of life, but in a way, these sort of things should not happen. And if the planning was respecting the underground and there was enough investigation and enough regulation and monitoring, these things would not happen. And modeling these quick clay landslides requires quite complicated computational models. So it is something which is in the research stage still. But in a way, we can do sort of quite broad brush things already. And these are sort of examples from our NordLink project together with colleagues in Norway, looking at landslide susceptibility. And we were using clays in Kvarm in Norway. And what we were taking into account is that there are a lot of slopes which basically currently don't fail. So all these dots are green where we've been running these simulations with Phoenix. So if we account for partial saturation, the slopes are there just like they are now. But if we basically have some sort of heavy rainfall event, then in a way, actually, the green areas become yellow and red, so we have caution. So we have problems. And actually, in this particular valley, when there was the last storm, there was actually hundreds of landslides. So we can start predicting it, but in a way, we need to know where to expect them so that and we need to understand the mechanisms better so that we actually can have early warning systems and things like that. And in order to do that, we really need to have physics-based models which we use for predictions. And then we need to combine that with monitoring the structures in real time so that we have basically a digital twin which we can continuously update with the measurements and then sort of keep correcting our models so that we actually know how things are progressing, and if something is about to happen, we can close ahead of time and everybody will be safe. So what is the outlook? I would say that the physics-based models which we can model these things are pretty much in place. So I think the only thing we have problems with quickly landslide is to sort of simulate how far it goes. So we can simulate when it's triggered, why it's triggered. It's very difficult to know when it's triggered, but of course by doing simulations and sensitivity studies, we can sort of get an idea how the system works. We also have techniques for upscaling, including those based on machine learning, and these ones really offer opportunities when combined with monitoring data. But the problem is, again, it is the lack of data, the quality of data. But in a way, and it is particularly true for when we talk about underground digital twins, because we are limited by open data. And one of the things is that there's a lot of data, but when I ask about data, I always get the PDF file. And I have better things to do than start digitizing PDF files. What we need is also well-documented raw data so that we can do our own interpretations. There is a lack of open source tools. I mean, the simulation market is very much dictated by commercial companies selling their products, which people are using, the consultants are using as black boxes. So that is something that we try to influence. And then there is sort of one of the things which we're limited by is a stakeholder involvement in setting up guidelines. And also greed, the business models that capitalize on public data. So we have a lot of challenges to overcome in order to really have sort of functioning underground digital twins, which would actually enable us to have sort of sustainable developments and also just sustainable continuation of living when the climate change is going to be upon us. Thank you very much.
You can stay. You can stay. I would like to ask all the speakers back on stage, and now we have a couple of minutes for a Q&A. So, are there any questions in the audience to any of our speakers? Maybe I can start with the initial question. We have been talking much about visualization techniques and so on. And you already touched upon that. Have you others experienced or have you spent much time on how to visualize the results? Because some of those are very complex, and how to communicate the results to stakeholders, partners, and so on.
Well, I can honestly say not so much. As you can see, I'm an engineer, so I usually compare curves against curves, and that's basically what we do. And I think the consequences are much easier to illustrate. I mean, you can illustrate mechanisms, etc.
Right. Thank you. Maybe.
I would say it's something we are working on, and it's from the simulations and from the data that getting out the actionable information for the relevant stakeholder. So we're working on it, but I would say I really acknowledged the morning's discussions where there's the sort of simulation teams, and it's the simulation that's important, and then you have the visualization people, but the visualization is important. And I think that's where this, if we get everything in a structured way, this will make it much easier, and we can get help, us engineers, with the visualizations, because it is really important. And in the role I have today at Ramble, it's a lot of discussions at a level it's often not even civil engineers background, people that are responsible for planning our cities and sustainability and all of those things. So it's really important that we have very simple, clear information with the message we want to get across.
Yeah, thank you.
So in CFD, for example, there are different methods to visualize the results. There are like contour plots, streamlines, but also from our experience, I think we have found out that videos seem to be more attractive to people, especially those who are not CFD experts, especially also because wind is something that is not very easily grasped by people, and it's a lot easier to be understood using videos, and it's a lot more attractive as well.
Thank you.
We have a question here, I think.
No, I think you brought up my question, actually.
Okay, happy to hear. Are there other questions in the audience?
Yes.
Hi, I have a question for Maha and Tara. So I think it's really interesting to see kind of research that's being done in industry. And what I wonder is if you could speak a little bit about how far or close is it to get these tools that you're developing into the hands of practitioners at the places that you work? Are they already using it, or what's the gap? And how do you kind of bridge that?
Do you want to start? Well, I mean, when it comes to the research and collaborations with institutes like Chalmers, for example, but we have other research collaborations also. I mean, obviously, a lot of that investment is in those individuals that are carrying out that research, and then that's kind of my job to get it into projects. So if we use Amadip as an example and the research I showed at the end there, we've already pitched in 10 projects and are working on implementing in 2 real-life projects, and it was finished just a few months ago. But it takes a lot of effort to explain, and there's a few sort of walls that you have to break down to get people to understand why you want to do things a different way. So it's a bit like we're talking about the valley of despair, or the initial barrier to get more to have test beds. That to start on that journey is also a challenge.
Yeah, and it is this where the stakeholder involvement is an important thing. You can get much better products if you are demanding it, but if you don't ask for it, you will not get it.
Yeah, and I would say from my perspective, I mean, this methodology was a bit advanced because it involves different tools and a long script that we have used and so on. But the important thing is the methodology, I would say, in general, because this is based, what we have done is based on also that we have tested other tools and we have realized that this is the best methodology that you can generate. So I would say at least internally from our sake, we are looking at using it more and more, but the people who would use it would need to have a bit of knowledge about all of these and all of this information. We have developed different tools at White for architects to do the same simulations, but in a simple way. But this methodology is not at that stage. But I also personally believe in open source information. So we are writing a paper right now about the methodology. Basically what I said, just written in paper, and we're going to publish it as well. So the script itself, of course, is not open, but the methodology is the most important, and how we have set up the model and what we were looking at, and so on, the conclusions, of course, and so on.
That's not open source, is it?
No, not really.
Are there other questions in the audience? No? Maybe I have one more follow-up question. I would like to touch on the interoperability, because we have heard so much about that. And I think you, for sure, have very many data sources that you incorporate. You have shown multi-domain simulations that also have probably different sources and different results. So, yeah, can you share your experiences on that?
Yeah, well, it's kind of one of the reasons why I started with the structure, because I mean, if I won't name names, but we've been at municipalities when they say we want to be digital, we want to be the cutting edge. And then we start asking, okay, well, where's your data? And okay, well, it's in a project there, in that map there, and in that one there, in there. The data's not available, and I think that's the most important part. It needs to be available, and then we can easily utilize. Like I showed, I mean, the LIDAR data was done for one purpose, and then because it was available, it was used for another purpose, a very valuable purpose, that otherwise might have cost a lot of money to try and to simulate. But if the data is not available, then it's very hard to be interoperable. So we need to have more data architects, I would say.
Any additions to that? No. Okay. I would like to close this session, and thank you very much to all of our speakers again.